Hi everyone, and welcome to my colloquium talk. My name is AayushiPramanik, and today I'll be presenting on the efficacy of non-pharmaceutical interventions on COVID-19 transmission. So just going through the agenda, I'll be starting with research question and some important terms. Then I'll delve into two different studies that have this research question of what the efficacy of COVID-19 NPIs are. And so the first study, which is Lai et al., will look at a network-based SEIR model, and the second study, Bronner et al., will look at a Bayesian hierarchical model. And then finally, I'll conclude and provide some further thoughts. So the main research question that both of these papers look to answer is how effective are government non-pharmaceutical interventions, NPIs, in curbing COVID-19 transmission rates and cases. So NPIs are essentially community mitigation strategies. So it's any actions apart from vaccines or medical related things that people in communities can take to slow the spread of an illness. So in the case of COVID, these NPIs could be hand washing, social distancing measures, travel restrictions, contact tracing, etc. And so the two studies I'll be looking at will have two different mathematical models that both focus on RO to estimate the effectiveness of NPIs. And RO is the effective reproduction number of the disease, which I'll talk about in the next slide. So RO essentially measures this level of contagion of the disease. So it's the average number of cases that an infectious person will cause during the time that they're infected. So for for COVID-19, the estimated RO is approximately 2 for a period of infection of 14 days. And so we can see that with the graphic on the left. The little figure in red is the infected individual. And once they cough or somehow spread the virus to other people, it's estimated that they'll spread it to 2 people who will then spread it to 2 people, and so on and so forth. And so this is how the disease exponentially increases. And so the idea is that we want to get RO to below 1 so that instead of the disease exponentially increasing, it's sustained instead. So the first paper we'll look at is by Lai et al. They use a network-based susceptible exposed infectious removed, or SEIR model, that focuses their study in China. So they look at 3 different groups of NPIs: intercity travel restrictions during the Chinese New Year holiday period, early identification and isolation of cases, and then contact restrictions and social distancing measures. They estimate 114,325 cases in mainland China as of February 29th, 2020. And they estimate that without these NPIs, the number of cases could have been 67 times higher by that February 29th date. They find that early detection and isolation of cases prevented more cases than did travel restrictions and contact reductions, but a combination of all of the NPIs had the strongest effect, and the timing of the interventions really mattered as well. So going into their methods, they look at epidemiological data and historical and near real-time anonymized data on human movement. So they have 3 different data sets on population movement. They use an aggregated and de-identified data set on near real-time inbound and outbound flows for each city in their data set. They look at a historical relative movement matrix and daily population movements at the county level. So they use this stochastic susceptible exposed infectious removed modeling framework based on travel. And stochastic basically just means that they use random variables for each of their observed values. So it's a randomized distribution. And they simulate the spread across 340 cities in mainland China. And within each city, they also estimate the number of SEI and R people per day from December 1st, 2019, and then conduct before and after comparable analyses to quantify the effects of these different groups of NPIs. So going into their model, which is a network-based SEIR model, they use daily travel networks to simulate outbreak and intervention scenarios for before and after analyses. And they essentially follow different time steps in which they sequentially cycle through infected, recovered, and exposed individuals to model the population. And then this approximates a deterministic continuous time model where C and R are varied over time. So just some of the basic terminology in terms of variables. So C in this model is the mean number of new infections per person. R is the rate at which infectious people are recovered or removed from the population. And epsilon is the inverse of the time spent exposed but not infectious. So looking at their deterministic continuous model on the right, they have 4 different differential equations. And so during each time step, infected people were first recovered or removed from the population at this average rate of R. And this was incorporated as a Bernoulli trial, which essentially a Bernoulli trial, again, is a random experiment with 2 possible outcomes. And they use a Bernoulli trial for each infected person with a probability of recovering of 1 minus e to the negative r. Then the model converts exposed people to infectious by similarly incorporating a Bernoulli trial for each exposed individual. And this daily probability of becoming infectious is 1 minus e to the negative epsilon. And then finally, this number of newly exposed people was calculated for each city on the basis of the number of infectious people in the city, so I, and the average number of daily contacts that would lead to transmission that each individual had. And they simulated this number of exposed individuals on a given day through a random draw from a Poisson distribution for each infectious person, in which that mean number of new infections was C, and then this C was multiplied by the fraction of people in the city that were susceptible. So in this way, they model the change in susceptible, exposed, infected, and recovered people over time. And it's kind of this backwards deterministic model. So you can see that kind of the terms in the change in recovered people are incorporated in the infected, which are incorporated in the exposed, which are incorporated in the susceptible change. So after the model completed their infection-related processes, the authors moved infectious people between cities. So they moved them from their current location to each possible destination, including staying in the same city, using Bernoulli trials. And they parametrized the probability of moving from city I to city J using Pij, which is the proportion of smartphone users who went from city I to city J in the corresponding day, from the Baidu dataset in 2015, accounting for travel restrictions in 2020. And with their simulation run, so they initially infected 5 people as the minimum number of infections that would prevent stochastic extinction of the epidemic during the initial days. But they also ran the model with 3 and 8 people, and they found that there was really no significant difference with these initially infected numbers, except with 3 people, 50% of the runs led to 0 cases after the first week of simulation. So that might be too small of an initial infected number. And finally, with their model, they reconstructed the spread of COVID-19 using data on population movement between and within cities. So they looked at smartphone users of Baidu location-based services, which is, I think, a popular service-based thing used in China. And they also looked at the data on delay between the onset of illness and reporting of cases across the country. So if we look at figure A and B, they both show relative outbound flows of travelers for different cities. So figure A looks at the relative outbound flow, which is unrestricted, which is the blue line at the top, which they estimated based on travel in previous years. And then the red line is the restricted or actual outflow of travel in 2020. And for figure A, they look at all cities in mainland China, but for figure B, they restrict it to the Hubei province. And for figure B, Wuhan is highlighted in the darker colors compared to the other lines for the other cities in the province. And so in A, we can see that especially between the dates of middle of January to end of February, there's really a drastic difference in the estimated travel that would be unrestricted if there weren't travel restrictions versus what the restricted or actual restrictions are. And we can see that after these travel restrictions are lifted outside of the Hubei province, the lines get a lot closer together, though the actual travel is still less than what it would have been in prior years. And then if we look at figure B, there's a similar trend, except once we get to March, it seems that a lot of the other cities in the Hubei province, travel goes back to what it would have been in previous years, but Wuhan's outflow of travel still remains really low this year compared to what it would have been prior. So Lai et al.'s results. So they look at the population movement and close contact, and they think that these have a major role in spreading COVID-19 within and beyond China. They found that the importance and the effects of their 3 NPIs differed. So improved detection and isolation of cases and social distancing measures had a greater effect than did travel restrictions. And they find that the country should consider partial continuation of these NPIs. So looking at some of the figures that they show in the results, I found these pretty useful to kind of illustrate the effects that they found. So in these figures, A, B, and C shows the effect of combined interventions versus getting rid of one of the interventions. for the city of Wuhan, and D through F show the same estimates for cities outside of the Hubei province in mainland China. But I'll kind of talk about all of the results together because there isn't too much of a difference between them. So if we look at A and D, this shows unrestricted intercity travel for the cities in Wuhan and outside of the Hubei province. And we can see that in A, the combined interventions are in blue, and the unrestricted city travel, so taking away this one restriction or this one NPI from the actual population, is in red. And we can see that there really isn't too big of a difference between them. So it seems that travel restrictions don't really affect this number of cases and this spread of COVID as much as would other NPIs, because the number of cases don't really change if we take away these travel restrictions. Then for B and E, we can see the same effect for unchanging the reporting and isolation of cases. So if we take away this NPI, we can see that there's actually a pretty drastic effect. So with combined interventions, the number of cases fall again after middle of February, but with unchanged reporting and isolation of cases, the cases actually continue to rise and then plateau at a much higher level, above 10,000 than they would have in the actual case with combined interventions. And then finally for C and F, again, we can see that unrestricting within city travel and contact would actually lead to an exponential rise in the number of cases. So this is, again, a pretty beneficial NPI. The authors of this study also look at the timing of interventions. So they use their data in their model to estimate the epidemic curves for interventions implemented either earlier or later than their actual timing. So for A, we can see that they look at what it would look like if NPIs were implemented 1 week, 2 weeks, or 3 weeks earlier than their actual timing. And we can see that compared to the actual number of cases with the NPIs, which is in the bright blue, if NPIs were implemented 1, 2, or 3 weeks earlier, the number of cases do drastically fall. So it seems that timing is pretty important, which we can also see in B, which looks at the inverse effect. So looking at implementing these same NPIs 1, 2, or 3 weeks later, and we can see that cases would then exponentially rise. So both A and B kind of show that the timing of interventions is really critical to the spread of COVID. And then finally with C, the authors look at the estimated spread of COVID for different rates of population contact after lifting those intercity travel restrictions. So in the middle of February, travel restrictions were lifted within cities in mainland China, and this led to a much higher rate of population contact than obviously existed before then. And so the authors estimate what it would look like if there actually was a reduction in population contact of 75, 50, and 25%. And we can see that this red line shows what it looks like in the actual case with no reduction. And there's a rise in cases again after these travel restrictions are lifted. But if there were a reduction of 75, 50, or 25%, the cases would actually continue to decline. So it seems that this NPI is actually pretty important to curbing the spread of COVID. So with Lai et al., some of the limitations that I found and that they discuss in their conclusion are that the model doesn't account for asymptomatic cases and mild infections. They really only consider the symptomatic cases, which is taking away this really important part of the population, because with COVID, a lot of cases are asymptomatic, so they aren't necessarily accurately measuring the number of cases. Also, other factors could have changed during the outbreak, and that could have confounded results. So seasonality, humidity, other factors that weren't necessarily NPIs that they consider could have definitely affected the number of cases, and that's a little hard to control for. There also are strong biases in the population coverage that Lai et al. Looks at. So the data only relies on mobile phone and Baidu data service users. So that doesn't include children, and it also doesn't include non-owners of this Baidu data service. So they really only look at a specific subset of the population. And finally, they only consider these 3 groups of NPIs. Obviously, with COVID, there's so many other non-pharmaceutical interventions that we could look at, and they only restrict to these 3. So it would be interesting to extend their study to other groups of NPIs as well. So the second paper that we'll look at is by Bronner et al., and this looks at a Bayesian hierarchical model. and they measure 8 NPIs across 41 countries. So they look at 34 European and 7 non-European countries and use a time and country-specific reproduction number to control for differences between the countries. And they model the effect of NPIs as a percentage reduction in the reproduction number R, and they have 8 NPIs, so mandating mask wearing in public spaces, limiting gatherings to 1,000 people or less, 100 people or less, and 10 people or less, closing some high-risk businesses, closing most non-essential businesses, and closing schools and universities, and then issuing stay-at-home orders. So we can see that this study is already a lot more broad and comprehensive than the lie et al. Study, and they focus a lot more on the reproduction number R in showing the effect of the NPIs. So they find that countries can reduce R to below 1 without issuing a stay-at-home order as long as they issue university and school closures, they ban gatherings, and they close high-risk businesses. But they find that closing most businesses only has a limited additional benefit, so it may not be necessary. So in their methods, they look at a data set that records NPI implementations when measures influenced at least 3/4 of the population. And their window of analysis began January 20th, 2020 and ended after the first NPI was lifted or May 30th, whichever one came first. They used independent double entry and cross-checked with public data sets, and they smoothed their data using a moving average on a linear scale over 2 days into the past and future. So as I mentioned, they use a Bayesian hierarchical model to model the effect of their NPIs. So just a brief primer on what the Bayesian hierarchical model is. It essentially is a prior distribution of model parameters that depend on other parameters. So it stems from Bayes' theorem, which says that the probability of theta given x is proportional to, that's what this little symbol means, the probability of x given theta times the probability of theta. So it's essentially this estimation of parameters depending on this other probability of a parameter that you already know. And so with hierarchy, which is what the authors look at, we can essentially look at distributions found in previous observations to construct this model. So this equation example that I've shown here is the simplest case with 3 parameters, but we can obviously extend it to as many as we want. So the left term before the proportionality symbol shows the probability of alpha and theta given x, and this is the posterior term, so it's the new prior distribution that we're trying to find. And that's proportional to the probability of x given theta and alpha, which is this likelihood of the data observation given these prior values, times the probability of theta given alpha, which is the sampling distribution, times the prior probability, which is the probability of alpha in this case. And so the authors use this model to essentially model the effects of COVID, as we'll talk about in the next few slides. So their model uses chronological data on NPIs in 41 countries between January and May 2020. And as I mentioned, they use independent double entry to cross-check their data. And they use this Bayesian hierarchical model to estimate the effectiveness of NPIs by linking the implementation dates of the NPIs to national case and death counts, which then they model as a percentage reduction in the reproduction number R. So this is the main graphic that they show, and it's pretty useful to kind of see the sequencing of their model. So in just a brief model mechanics, the purple nodes are essentially observed or have a fixed distribution. And looking from bottom to top, at the bottom we can see the 8 different NPIs and the growth reductions alpha of I. So that essentially shows the effectiveness of each intervention I, and that's represented by this alpha of I. And they use case and death data from each country to backwards infer the number of new infections at each point, which is then used to infer the reproduction numbers and then the NPI effects. So using this alpha of I, which is the effectiveness of each NPI, they combine that with this phi of ITC, which is this dummy variable that indicates whether the NPI is on or off. So phi of ITC is 1 if intervention I is implemented in country C at time T and 0 otherwise. And so combining these alpha of I and then this phi of ITC and multiplying them gives the product of active reductions. And then this is used along with the basic reproduction number ROC, so at time T equals 0. Both of these are combined to get to the daily reproduction number RTC, which is the time and country specific reproduction number. And then this is transformed into the daily growth rate. And so during exponential growth, which is what the early stage of an epidemic is, there's a one-to-one correspondence between the reproduction number and the growth rate. So they use this one-to-one correspondence along with this incorporation of the generation interval to estimate their daily growth rate. And the generation interval is the time between successive cases in the transmission chain. And so then from their daily growth rate, they use this to estimate the number of new infections, NTC, and they look at the infections in terms of new confirmed cases and new deaths, and they also incorporate a delay from infection to confirmation or death. And they do this process for each country C, so each of the 41 countries in their sample. So zooming into parts of the model, we can see here, this is just zooming into the 8 different NPIs and showing that this alpha of I is just showing the effectiveness in the growth reduction of this intervention. And then zooming into the kind of cause and effect chain. So again, at the bottom, we have this product of active reductions, which is then used with the basic reproduction number to get this daily reproduction number RTC. And then that one-to-one correspondence gets us to this daily growth rate. And that correspondence depends on this generation interval, which we assume to have a gamma distribution with a mean of 6.67 days. And then, as I mentioned, they model the daily new infection count separately for confirmed cases and deaths. And these are translated into reported confirmed cases and deaths after a stochastic delay, which is assumed to be equal across countries based on prior empirical data and distributions. And they are both gamma distributions that they use to estimate these. And finally, using a Markov chain Monte Carlo sampling algorithm, this model infers the posterior distribution of each NPI's effectiveness while accounting for cross-country variations. So this just briefly shows the model mechanics to get to this time and country-specific reproduction number RTC, which then determines the growth of the epidemic. So we can see that it depends, again, on this basic reproduction number ROC, and then this product of this NPI effectiveness term. So we can see that the effectiveness of NPI I is represented by the parameter alpha of I, and each NPI's effect on RTC independently affects this term as a multiplicative factor. So again, this phi of ITC is this dummy variable, which when multiplied to the alpha of I gets us to this product term that can help us find this time and country specific reproduction number. Then looking at the infection model, so M is the moment generating function of the distribution of the generation interval, which again is the time between successive cases in a transmission chain. And they model new infections that will either be subsequently confirmed positive, so the confirmed case is C, or lead to a reported death, so the confirmed deaths D. And they have these 2 different equations here showing for cases and deaths how to calculate this new number. And they're essentially the same other than the cases and deaths. So I'll just focus on the top equation here. So in an early phase of an epidemic, NTC grows exponentially with a daily growth rate GTC. And it depends on the number of new infections at time 0, so N0C, times this product of 1 plus the growth rate, G tau C, times the exponential term that has to do with this stochastic delay. So that's kind of how they derive their number of new infections, and that's how they then estimate the effectiveness of these NPIs. So looking at their results, their effectiveness estimates are interpreted as the effectiveness averaged over the context in which the NPI was implemented. So their results are very context specific. So it really only is applicable in the context in which the NPIs were implemented. They find that closing high-risk businesses is a more promising policy option than closing most non-essential businesses, and that provided that other NPIs, namely closing schools and universities, high-risk businesses, and limiting gathering sizes stay active, a typical country can reduce R to below 1 without issuing a stay-at-home order, which has pretty important policy implications. So looking at some of the graphs that they use to show their effects, again, this was really useful for me to just kind of parse through the effects of the different NPIs. So this essentially shows a different bar for each of the 8 NPIs they consider, And they show the effectiveness as this average additional reduction in RO in a percentage form as observed in the data. So before I go into a little bit of detail, they show cumulative effects for hierarchical NPIs, so gathering bans and business closures, and they show the joint effect of closing both schools and universities because the dates of schools and university closures perfectly coincided almost, and they couldn't meaningfully isolate their individual effects. So if we look at this distribution, we can see that there are definitely certain NPIs that are more effective than others in reducing RO, but they all have a positive reduction, so they're all effective in reducing RO, at least slightly. It seems that gathering limited to 10 people or less, closing some businesses or most non-essential businesses, and closing schools and universities are the four most successful NPIs in reducing RO, whereas mask wearing, limiting sizes to larger gatherings, and a stay-at-home order are not as successful. Then looking at the combined NPI effectiveness, so here we can see the main crux of the author's conclusions. So on the left, there's a chart that shows the maximum RO that can be reduced to below 1 for each set of NPIs. So essentially what they do is they start at the bottom at an RO of 1, and they keep layering NPIs on top of one another to see with all of the NPIs what the maximum RO can be found that could be brought below 1 with all of the NPIs implemented. And they find that RO can be almost at 6 and still be brought to below 1 with all of the NPIs, which is pretty impressive. And then on the right, they show the combined effectiveness of all of the NPIs to bring R to below 1. So obviously, a lot of these NPIs were implemented around the same time frame. So it's a little hard to parse through their individual effects. So the authors decided to look at a lot of them combined together to see how they would affect RO. So they began with an RO of 3.8 based on previous empirical data. And they found that with all of the NPIs implemented together, it could reduce R by 82%. And starting from RO, the estimated R can be reduced to below 1 by closing schools and universities, high-risk businesses, and limiting gathering sizes, which is a very important thing when looking at future closures and things that we may need to do to curb the spread of the disease again. So looking at limitations of this study, so the NPI effectiveness depends on the context of the implementation, which is definitely something that isn't necessarily applicable in all terms. So it's very country specific, time specific. So it's a little questionable how effective their study would be when applied to any country or any context. RO may have also been reduced by unobserved NPIs or spontaneous behavior changes. So I kind of mentioned this in the Lai et al. Limitations as well, but RO could have been reduced by any like unobserved behavior, changes in seasonality, things like that. And then the results of this study can't be used to predict the effect of lifting NPIs. So they mentioned this briefly in their kind of warning signs at the end of their conclusions. So for example, closing schools and universities seems to have greatly reduced transmission, but clearly that doesn't mean that reopening them will cause infections to soar. So it's not really an inverse correlation. And finally, like the Lai et al. Study, several NPIs were excluded from this model as well, namely testing and tracing and isolation, which are definitely important parts of a cost-effective policy response. And they didn't include those, so it would be interesting to see how their RO numbers would change and how we could reduce it to below 1 with including these additional NPIs. So finally, my conclusion, I looked at a Lai et al. And Bronner et al. Study, which looked at 2 different models and 2 different scopes to look at how NPIs could be effective in reducing this reproduction number RO and curbing COVID-19 transmission. Both of the studies found that a combination of NPIs is most effective to reduce RO. Lai et al. Found that a timing of interventions is also really critical. And both studies found that certain NPIs are definitely more effective than others. So looking at some extensions of this, one big question that I found when reading both of these studies is just what level of compliance is assumed for the NPIs that they look at. So for example, like what are they assuming about mask wearing? Obviously there's a lot of people who don't wear masks correctly. Like how many people do we think are actually wearing masks in the population that they look at? and how do they define these interventions? So that would be an interesting thing to look at for further investigation. Also, when I was reading further into this question, this research question that I looked at, I found a few articles on whether the role of NPIs is overstated. So whether or not these unobserved behaviors or seasonality things that I discussed in limitations how much that actually does affect COVID-19 cases, and whether NPIs are being relied on too much. So that could be really interesting too. And finally, how do masks alone curb COVID-19's impact? So just looking at countries that implement masks versus those that don't, how have their COVID-19 case trajectories increased or decreased? How do they compare, and how do masks play a factor in that? And then just concluding with the big question of which studies really matter. So obviously there's a lot of uncertainty with COVID right now. It's a rapidly evolving disease, and we're learning new information every day, and there's so much that we still don't know. So the data is rapidly changing too. So just always keeping in mind, which studies can we actually trust, what data is important and relevant to kind of making a difference in policy implications is something to always keep in mind with any of these studies. So finally, I would really just like to thank Lai et al. And Bronner et al. For both of their papers. They were really interesting to read, and it was really cool to read about the modeling of COVID during this time when the disease is really rapidly evolving and so relevant to our population today. I would also really like to thank my colloquium advisor, Professor Miller, for introducing me to this topic and helping me along the way, and for his really great mathematics of pandemics class, which kind of got this idea in my head anyways. It's been really interesting to learn about mathematical modeling in terms of COVID. And finally, I would really just like to thank you all for watching this talk. I really hope you enjoyed.